hadron polarizing lambda.
Yeah.
More probable nuclear structure. Basically, it's going to cover things about RHIC, Belle, and
yeah, selected topics, I would call it. Yeah, thank you for the word. What does that mean?
Unless someone is
okay. So every time I come here and enjoy myself tremendously. So I'm going to talk about something which I call novel probes in nuclear structure, so in particular dihadrons and polarized lambda channels. And so the motivation is basically what we already heard here quite a bit from Tuna and Ralph, namely that we are interested in fermentation functions because they basically provide us a pathway to get from the properties of the hadrons that we measure in the final state to the quantum numbers of the quarks in the initial state that we are actually interested in. So we also saw in Gunnar's and Ralph's talk that pretty much most information we have, so the most well-traveled path is to look at single scalar hadrons in the final state, so pions and kaons. So in particular, if you look at this whole possibilities of this matrix of fermentation function, you saw it similarly to PDFs. Basically, just populate here this first row where we have the spin average hadrons in the initial state, so in particular the unpolarized fermentation function, and since not so long ago, also the transverse polarization dependent Collins fermentation function to access transverse spin structure of the nucleon. So this talk, the idea of this talk is basically have the same motivation that we usually give if we want to explain nucleon structure to outside people, namely that if you really want to understand something, it's a famous phrase, now add spin and see if you still understand it, and just basically move that to hadronization. And so the two things I want to talk about is a really polarized final state. So in our case, of course, it's lambda because it's self-polarizing decay. But the other thing is where kind of like analog are the hadron correlations, where you have instead of like a spin polarized final state, you basically have orbital angular momentum in the final state. So this allows you to do several things. On the one hand, so you can explore spin orbit correlations in hadronization, very similar to what you do in PDFs. The additional degrees of freedom you have now at your disposal also allows you to have a more targeted approach to extracting the nucleon structure. So examples are our extraction of transversity and also E of X, the hadron channels, which are much more clean than in the single hadron channel. This basically is, enabled by having these new fermentation functions that come into the game. So I think in terms of the topic for this workshop, I think this is an obvious relevance for the ESC, where we're both interested in hadronization as well as the nucleon structure. So here I will mainly talk about results from RHIC, Belle, and plans at JLab and Belle, and also point out all the measurements we can still do with the data that we have on tape, for example, at the STAR experiment. So let's see what happens to this landscape that we had earlier if you add polarized hadrons in the final state. So basically what you see is you get a matrix which looks pretty much identical to what you have in the PDF sector. So you have all these analogs to like WORMGEAR and all these nice functions giving you different correlations. So I concentrate here, unfortunately, only one of this. So this picture before should be a motivation to look into this more in the future. But just because experimentally relevant, or we have actual results, is only this one here, the polarizing fermentation function that describes the production of a transversely polarized hadron from an unpolarized quark. If we now move to the dihadron sector, we can do a pretty similar game and sort them in a similar way. The difference is, as was explained to me yesterday, Marco, is that we can't populate this part here due to parity invariance. So we're left with the functions here, but they're still very interesting. So here on the bottom, you have the IFF, so the transversely polarized quark goes into a hadron pair, which allows us to access transversely in a collinear way. And then we have this other function, here's G1 perp, which I would call kind of the WORMGEAR fermentation function, which gives me the sensitivity of the two hadron pair to the helicity of the initial quark. And that is possible because this is a TMD, so only by introducing the TMD I can get this correlation between helicity and basically the transverse angular momentum in the final state. So I also want to add that IFF, so the hadron fragmentation functions, are different from single hadrons also in the way that you can carry away really arbitrary units of angular momentum. So it means that you get like kind of towers, infinite towers of fragmentation function, and the way we usually deal with that, and I'm sure Mark will talk more about this, we do like a partial wave analysis in this decaying theta in the two hadron system, and then by that classify basically the different contributions. So here, and I won't really talk about this really in much more, we usually only look at the first term, which is the SP interference term, which usually dominates the cross section. Oh, so okay, I'll talk more about this. So basically, so it's a tenuous relation. So basically, this is related to the jet-handedness function that was kind of introduced more way back then. And so they introduced that as basically a way to probe. So it's related to this negative effect. So you can cut it to instant zones of sphenerons in the quark, it goes out, flips the helicity, and get correlations which are supposed to be sensitive to that. Okay. I think so I think the relation, no, so this way comes through this connection to the jet-handedness. So if you look at Margaret Alexander's original paper and Efron's paper, then you can see that there's some connection with them, super direct. But it catches people's eyes, as demonstrated right here.
Is it
this is longitudinal quark polarization, this is transverse. Oh, here you mean. So
it has to be in the middle column then. It's the future.
So I don't quite understand your.
If it has to be in the middle column, then it's
yeah, the middle one.
No, I think
okay. Sorry. Yeah. So I think okay. Sorry. Okay.
So ISO is not too far.
Right. So this should be here. So okay. Sorry about this. Okay. Fine. In any case, still a WORMGEAR.
So that one is called H1T. If it's in H1L, so if you put there, it's so it's like non-dream forest part, but the hadron is
right. That would be here. Yeah. Okay. But I mean the G1 perp is just I put it in the wrong matrix because I confused myself with the hadron patterns. Good. So in any case, so having set the stage, so the first thing I want to talk about is the hadron measurements RHIC. So first of all, it's something I'm interested in, and maybe not too many people know about. We have some new results. So I will repeat some of the things that Elko we talked about. Namely, the advantages of using the hadron correlations in BP, or the advantage of BP in general, is that you can go to very high scales. So you have, compared to CIDIS, which is plotted here, Hermes and Compass, you have up to 2 orders of magnitude higher Q square. You're still sitting in the valence region. You have no U-port dominance, and you have access to gluon contributions. The specific advantages of using the IFF in this case is that it's a very clean measurement, very similar or kind of the same as the CIDIS one. So in particular, you're in the collinear framework, and you don't have to reconstruct jets, which reduce your jet systematics and also increase your statistics. So if you compare, for example, our Collins measurement with the IFF measurements, the actual measurement is also the same pretty much as you do at CIDIS. So you basically look at these asymptotic correlations of the hadrons in the final state, so the asymptotic dependence of the angle between the hadron plane and the spin plane of proton, and you measure these asymmetries, which are then directly sensitive to transversity times IFF. So we already saw this. So the detector which we're doing it is STAR. So in particular, we use STAR has this very big time projection chamber, which allows us to do high precision tracking, in particular in the central region, and also PID with DDX. So all we do is a very simple measurement. We just take identified pions here from the TPC and do our symmetries. So some time ago, with a limited set that we took in 2006, we published this PRL, which was at that time we claimed the first observation of transversity effects in PP. Now, of course, we know that AN is also very tightly coupled to that, but nevertheless, these are beautiful results, I think. So you see here the binding with eta, which is very sensitive to the X region. So you scan your X, you go up here quite linearly, and you see so symmetries rise basically with X. And then the other typical variable that we usually look at is the invariant mass distribution, so it's invariant mass of the hadron pair. And you see this peak around the rho mass, which reinforces this model prediction that most of this comes from this P interference. We also have several much larger data sets on tape. So here I just want to show the comparison with 2012, where we just unfortunately only have preliminary results so far. These are these data points here compared to 2006. So we have more data points, and we have incredibly small error bars, which is of course, I mean, a precision that is higher than we have so far at pretty much any CILIS experiment, I think. And we have 2 times more data of this still on tape, just on 200 GeV. Then the most recent result is actually first letter B. It just came out in the beginning of this year. Is the measurement at 500 GeV now. So here on the left, I show you the invariant mass dependence in each panel, binned in the PT. So this is just for the forward rapidity, where in the higher X range we have larger symmetries. On the right side, it's for different PT bins in each panel, the invariant mass dependence. And again, you see this kind of typical behavior that we see almost a linear rise in PT. As it's higher PT, you access higher Z and X, and then we see these enhancements, so rise in invariant mass as well, on the forward direction, and this peaking around the rho mass corresponding presumably to this interference between the S and P waves. The other thing which is quite nice with these results, that if you plot them at the same PT or square root S, which kind of normalizes us to the same X per K, the results of the 200 and 500 basically are bang on each other, which is kind of expected because, of course, the evolution is very weak here, just because the scale difference is not very large. Transversity evolution is weak, and you have a linear deglap, so we don't expect much, and that's kind of what you see. And of course, it also shows you that the experiment is consistent. The measure is consistent in 2 energy ranges. I also, so I have it here on this slide, want to point out that the long run that we just had to do the W. So this 500 GeV data set used here is the same one that has been used for the first WAN results. Of course, now we took this very long run to do that precisely for the IVF. It means we have, I think, at least a factor of 15 more statistics at 500 GeV, which of course will allow you to have a multi-dimensional super precise measurement of that as well. So this shows the eta dependence, it's the same. What is new in the 500 GeV results is that we also looked at the same sign pair. And the reasons, so this is now for per plus and per minus. And the reason we did that was also, again, test this interference hypothesis. So if you have same sign pairs, of course, they can't come from the row, and as you you would expect, you see
same sign.
Same sign. So
Sign.
Yeah. So we order them by their momentum in this case, and you see you get 0 symmetries as you would expect. But and it's still ordered, no? The momentum ordered. So they're not randomized in this case, you know. So I guess so they're 0 as you would expect for different reasons. And the other thing I want to point out, so you don't see it here, unfortunately, again, not through the projector. So this shows you the comparison of our data with theory predictions from Marco and Alessandro and so on. So Marco is going to show you extraction of transversity from our 2006 data, which is of course one with the giant error bars. So I put this plot in here to show what the impact of our more precise data is. And if you, so basically the uncertainty band of the theory goes, kind of like this. So which kind of gives you an idea of what the impact on this data will be on the transversity extraction. Okay, so this is IFF as a collinear tool to extract transversities, in particular in PP. So the next thing I want to talk about a little bit is to use Dihadron correlations to access this functions. So we had some discussion already day before yesterday, I think, the slides that Aurora put up. So this is just a small recap. The one thing, so there are several interesting collinear twist 3 functions that we can measure. One of those is E of x. So there are several reasons why it's interesting. So Aurora pointed out the scalar charge. For me, also, this is just a connection to quark-gluon correlations inside the nucleon is interesting because it's kind of like the physics we go with the ERC. The nice thing also in pretty much all model predictions, as you see here, compared to G and F, the twist 2 for PDFs, E of x is relatively large, so we expect quite big results. The traditional way of accessing it is in single hadron production, where you have this rather complicated terms. We have like 4 different terms contributing, which presumably can all contribute at the same order. So this is in asymptotic relations of beam spin asymmetries. So here you see again that the dihadron fermentation function allows you much more targeted access. So if you look at the dihadron asymptotic asymmetry here, you reduce this to 2 terms, so E of x times the IFF that I talked about earlier, plus this part where you come to this twist 3 fermentation function. So they have different kinematic dependence, which presumably allows you to maybe disentangle it as well. So Aurora wrote some write-up some time ago where you can see all the details. So I'm not going to talk too much about this. So from an experimental point of view, I want to point out that these asymmetries have actually been measured at class 6. So these are with 2 different targets, and you see consistently large asymmetries that you see, which is of course always nice that there's actually something to measure there. So later when I talk about class 12, I'm going to show projections for class 12 and talk about the plan there. So first I want to move on now to this other dihadron fermentation function I had earlier, which I called probably wrongly the WORMGEAR fermentation function. And so this actually has a fairly interesting history. So as I said, it was first suggested to measure that by Diabur, Jakob, and Marco in this PhD some time ago, when you also find this connection to the jet-handedness. So this is here the connection to the jet-handedness by Efremov and Kaziev from '96. So we actually went out and measured that, what they proposed, and it turned out to be exactly 0, which was a little bit disappointing. And it turned out that there was actually a sign mistake in this calculation, and the Adelaide group did a new calculation pointing out how to measure it. And the main difference basically, so this is a TMD. So in this paper, for some reason, I thought we can kind of ignore this phi h angle, and it turned out to be still interesting. So the Adelaide group worked quite a bit on that, and not only did they do the new calculation and observe that I talk about, but in particular, they worked quite a bit on this NJL jet model, where they basically proposed a microscopic mechanism how these asymmetries come about. And it's for me super interesting because if you measure size of a symmetry, you can compare with that, and then you have a connection to like microscopic mechanisms of spin orbit correlations and hadronization through this model, which I find very neat. And as a side effect, they also predict quite sizable symmetries. So roughly a third. So here in black, the G1, and then the other one is the IFF. So you roughly have a third of the magnitude. So it should be measurable compared to the transverse spin stuff. So symmetries are there. So this is what the observer there propose. I don't want to go through the detail. I just want to point out that the main difference is that so far our Belle symmetries usually look at these phi r angles, but now it also comes in the asymptotal angle of the hadron sum. So this is kind of a sign that, you know, really measure TMD. Similarly, they're proposing something new on CIDIS, along the same lines. So this phi H, phi R correlations, and they also propose weighted asymmetries to break up these convolutions. So the last thing, which I think hasn't mentioned here at all, which you can do in Dihadrons, so in particular at CLAS, is to look at the target fermentation function. Am I completely out of time? No, not quite. Target fermentation functions. And so here, so we already saw from TED that there's some interest in accessing a fracture function. So the role of dihadron correlations here is kind of interesting. So what you can do is you can correlate a hadron from the target fermentation to one in the current fermentation. And what that allows you is to extract chiral-odd fracture functions here, and also access more of the flavor structure of the fracture functions. So this is also quite an interesting measurement that we can do quite well at CLAS, because we have good coverage in the central region. We have presumably this target hadron coming from as well in the forward region, where you get the current fermentation here. Okay, so having kind of motivated dihadron measurements, I want to go a little bit into plans. So all the stuff I talked about here, so in particular the beam spin asymmetry, also fracture function, we plan to do at CLAS. So probably see it. So CLAS12 is just start data taking at the upgrade JDAP12. So this is a photo from the hall. So these pictures are always kind of like confusing to me because everything is so closely bunched together. I think it's worth pointing out that we have a forward detector, so we get all the stuff from the current fermentation region. We have tracking as well as PID and electromagnetic parameter. And we also have a central detector where you cover basically the target fermentation region quite well as well. Where we also have some sort of PID and tracking. So KRI coverage. So I think the first day we discussed it quite a bit. That is of course somewhat limited by the beam energy. However, it's not as bad as some people make it seem. So this is X per K and Q square. So you see we have quite some phase space at somewhat higher Q square, of course, pushed up to X per K. And also in the CIDIS region above W of 2, we get quite a bit of data. Yeah.
Also the
Lambda cuts?
Is this X-Q square plane also if I want to detect the lambda?
I have not looked. This is just for the CIDIS, basically. That's just CIDIS, yeah. Lambda is, I talk a little bit about this, but it's Alex, but this is for now CIDIS.
Then suddenly you also get a minimum PT and things like this, which cut, of course, in your X-Q square plane significantly.
Well, Lambda main problem is the minimum PT on the pi, and that's often gets lost somewhere. Exactly. Yeah, but okay, that's So I show these plots because they have been shown before. It's been 2018, so I didn't want to generate my own one because I have some other problems. But the point is, if you see usually these plots from other experiments, it means that this stuff, it looks nice, but you never get statistics here. But the nice thing about JLab is that we have so much statistics that we actually populate the whole thing. And there's an example, so it's also from SPIN 2018. So these are beam spin asymmetries of single hadrons taken by CLAS12. That is one single day of data taking. So I would argue that it's actually comparable to the data that maybe all of them is data in terms of precision. It's just one day. So you see here the pi plus beam spin asymmetry. So this gives you an example of the statistics that's collected. If you look at the dihadron asymmetry, so for example, the sensitivity of E of X, so these are the projections. So the yellow stuff comes from model uncertainties. I actually believe that's something Aurora calculated some time ago. So it's not really, it's not the systematics of this measurement, so it doesn't show it, and they're plotted at the mean of these models. So the statistical error bars are not visible, so here's a pi plus, pi minus. It's 54 days of unpolarized proton, which is approved in the first one, K plus, pi minus, also very nice error bars. And this is the target spin asymmetries of similar uncertainties on polarized. So you get incredibly precise data, and I also want to mention, because I talked to Matthias this morning about this is sensitive to the +3 function HL. Just another outlook is, so we heard a lot about Belle, so I don't want to repeat any of that, so Ralph did a great job to talk about this. I just want to remind you that on the fermentation side, so if you saw, for example, the channels of pi k, of course, that we haven't really measured plus and minus yet. So the outlook is, of course, Belle, but I also want to remind you that we have no Belle 2 running. We upgraded our collider so don't worry about the details. I just want to point out we have now 40 times the luminosity. We upgrade our detector. The main impact is that we have now much better tracking. We have state-of-the-art PID, especially for kaon channels. We now go up to a much higher precision than before. And also there are many other improvements that we had to do basically to counter the increased background. So we actually already took data. Phase 2 of Belle 2 is completed, which was mainly commissioning, and then in early 2019 we start phase 3 with full vertex detector and so on. And the ultimate goal is 50 inverse attopines, so it's 50 times the statistics of Belle collected till 2025. So within 1 or 2 years we will have surpassed the Belle statistics, which is presumably better quality data. So this is one of the first events. Here, QQ bar events, you see everything looks nicely tracking. Okay, and this is from the first data reconstructed JPSI. So you see that we already saw data. Can already reconstruct some hadrons here, which shows you that it's a running experiment. It's not like something that's in the future anymore. We're taking data basically right now. So this is just before I come to the Lambda in the last 5 minutes. This is just an outlook on the DI-HADRON channels at RHIC, Belle 2, and ERC. So I think the first thing, of course, to point out, RHIC and ERC measurements are really going to be very complementary in terms of what you can do in terms of flavor structure, and so on. There are many exciting possibilities. Of course, transversity is kind of obvious. There's still a ton of more data from STAR in particular. We have to extract the unpolarized cross-section for the gluon fermentation function. TRIS3 function should be possible at RHIC and also at ERC, which would be very, very interesting, basically through dihadron correlation with longitudinal polarized beams. This WORMGEAR G1 perp similarly should be accessible at RHIC and ERC, and it would be interesting to check universality and so on, because theoretically are even. There are other dihadron channels, for example, Mulders you can do. There's some hope, I think, that you can decouple a little bit more from the Kahn effects in the single hadrons by measuring a smoother relations around pH. And so we also plan to do it at CLAS12, and of course at Belle 2 will contribute a lot to the position extraction of the dihadron fermentation functions for ions and kaons.
Can you say something?
Can you say something about velocity? I haven't thought about that. Huh? Oh, you mean the press velocity? So WORMGEAR here, I was referring to the fermentation function. So is there a press velocity fermentation function? I'm not sure. Yeah, I mean, it's certainly with the lambdas.
It should be zero. So you should produce a lambda from understanding. Produce a lambda transversely polarized, starting from a transversely polarized from a quark. But how to distinguish this from the capital H1, which is, I guess, the object that describes this fermentation? Because if you want an analog of its velocity, you need something that I should write it as H1T.
Should I go through my lambda slides first and we discuss these kind of things? Because it's still some nice. Okay, lambdas. Okay, I save myself motivation. The main thing is which structure I will point out. The long-standing question how the lambda correlation actually comes about. We have a lot of data. I want to point out most of this PP becomes instantaneous fermentation in initial state. Also, most of the PP data here is at fairly low scales. We need the class sensitivity measurements. Huh? This is taken from the Atlas paper, the conversion. Yeah. So I just did that because it's a nice plot. So they measured this stuff, which at central pretty, which is 0, but they also put the other one. So I have no idea why this offset is here. Of course, these are nuclear targets, but some of them are bang on, other similar energy.
They are totally different energies.
So yeah, in any case, that's just my motivation. Big asymmetries. This is the Atlas paper, which is this reference here. So it was only natural to look at this in plus and minus, and so this is very new results we just submitted to PAL. We haven't heard back yet. So what we did is we measured the lambda polarization. So this is so many people ask me if this is like the simple interest B approach with respect to the beam axis. No, so we define the lambda plane with respect to either thrust axis or hadron on the other side, which was a suggestion by the paper of Feng, Zhongbo, and Werner et al. So this is what we measure. So it's a PT of the lambda in different Z bands, and the transverse polarizations. We see that we get relatively large asymmetries, which rise mostly with the PT, but not here in this middle Z band, also with Z. So we'll talk a little bit more about this like peculiar dependence here in this middle Z band, which is probably maybe related to the flavor structure there. But summarizing, we see for the first time large asymmetry for the lambda polarization in the fragmentation region. So as I said, the first time we saw that, we were very surprised by this PT dependence like flips here, but still not entirely clear why that is, and I think we should do Sidis measurement to confirm this. One hint is if you look at the flavor that goes into the lambda at this point, and what you see in this region is, so at higher Z, it's mostly strange quarks here in blue and some charm. So at lower Z, you have more U quarks as well, which possibly dilute this if you think that the polarization may be carried by the strange. So what happens here is that the charm fraction increases and the U section goes down a little, and the strange kind of decreases a little bit. So it's still peculiar it goes down because you go to higher PT. So maybe the U quark carries some of the polarization that also goes down, but it seems to be quite correlated to this flavor structure here. And then the anti-lambda, the analog thing happened, and you see the same structure. Even though here we see, as you expect, going to 0 as in PT, to 4 PT with 0 again. I also want to point out, and I think that's the first in general in lambda physics that we were able to correct for feed down from sigmas as well as from charm. So it's a little confusing these plots, but basically the prompt lambda is the result of these blue points here, so they are corrected for this, so you get somewhat larger symmetry. The lambda from sigma seem to have the opposite correlation as you'd expect from angular momentum conservation. But in general, these are relatively large error bars. Of course, at Belle 2, we could do this much more precisely. And these results, these relations might also help you to correct for feed down, I think, in other configurations like at ERC at RHIC. So as mentioned in the paper here by Daniel, Zhongbo, Werner, and Feng, where they basically propose this lambda as a test for universality, because in this case you have a chiral even T-odd function, which is kind of like a first in fermentation sector, because usually the other T-odd function you know is a Collins function, which is chiral odd, so you always, it's difficult to pin down the sign. The measurement that was proposed there is to look for meson on the other side, so you have plus minus or k plus k minus, basically to disentangle the flavors some more. These are our results. So here we have a spindle Z of the pi on each panel. This is different lambda Z's. What you see is as you go to higher lambda Z's, the symmetries kind of go close to each other, presumably because the hadron on the other side is not so important anymore, because you look at the Z of the lambda. Whereas at low lambda Z, you see big differences if you have a pi minus, so you have this positive Z, or a pi plus on the other side. And the kaons basically the same picture in reverse. So this is actually quite different to what the prediction was from this paper here. So you see the same sign for both charges. So we look again at the flavor decomposition, so that might give you a hint again. So as you maybe expect, so in the back, you basically are dominated here by the anti-U, because the U goes into your pi, and whereas if you have a high lambda Z, you're dominated by the Z, by the strange quark, because you produce the lambdas. The thing is though that for the two different pion charges, you see that even though the symmetries you get in the end are very similar, the flavor contributions are actually quite different in terms of strange. Of course, there is some difference here, but it's still kind of peculiar to have, at least in the Monte Carlo simulation, so much of the U-core contributions here, and still the symmetries are somewhat similar. So it's still a little bit of puzzling dependence. The same for the kaon, basically gives you this mirror image. So again, but this time you have actually almost exclusively the strange quark. Here the separation, of course, also becomes much clearer. And also here for the K plus, on the other side, you basically have exclusive strange quark going the lambda, you get very large asymmetries, when here on the other side you have more of the U-corpses, which are smaller. So it makes qualitatively some sense in the details maybe have to be worked out. Yeah, so the echo is saying lambdas at class, difficult, it's a plan. We had a lambda physics at class 6, but mostly targeting exclusive production. Class 12, if you just look at the, sorry, 2 more slides. Look at the semi-inclusive lambdas and you want to be in the current fermentation region. So this is the XF distribution just for Monte Carlo, and it's like a tiny bit of statistics, but maybe from a day. You see that in principle for XF greater than zeros, so these are lambdas that are in principle reconstructed in the class acceptance. So both the pion and the pion proton channel and both the class acceptance. You get something, if you just restrict yourself to XF greater than 0, you get some lambdas. We have to figure out how, if that's really possible. So I started looking at it a little bit. So right now reconstruction is still terrible, especially low PT. So we don't really use all these panels. So the hope that we cover those, and actually you can look at lambda polarization where you are barely in the current fermentation region. So I'm hopeful, but it's far from clear. And the goal would be, of course, to compare that with the plus and minus, both to understand the flavor structure as well as these interesting behaviors. So if you just take the geometric exception, you actually get a lot of lambdas. But this is, of course, kind of fantasy word. Okay, so I just have 2 outlook slides. So, okay, lambda physics at RHIC here seen there too. I think it's pretty exciting opportunities which haven't really been explored too much. So the obvious thing is to probe the flavor decomposition of the polarizing fermentation function at ERC, test universality, access transverse equilibrium array with the transverse polarized transverse polarization dependent number is H. And I think many, many more. We can look at all these correlations in the final state. I think you can use precision Belle data, maybe also ERC data to correct for feed down. So at Belle 2, my hope is also to look at correlations between the transversely polarized lambdas of both hemispheres, as well as lambda correlation with simulant dihadron. And at RHIC, I think it might be interesting to look at the polarizing lambda from unpolarized protons and jets. We maybe get around this problem that you don't have acceptance in the forward direction where the correlations are large. Presumably, if you look into a jet, it should also be large. Summary and conclusion. So I think both of these channels, by including polarization in the final state, allow you to have exciting opportunities to look, learn about the nucleon structure and also hybridization, particularly spin orbit. Spin orbit correlations, there's a ton of stuff to do with existing star data, class 12 and Belle 2, of course, on the horizon, it can do interesting stuff. In ERC, many of these measurements will be really impactful because they're clean, they have high scales, and so on. So I mean, encouraged to explore this kind of physics more. And one place to do this, so now I need everybody to wake up, is that we will have a fermentation function workshop at Duke University. So organizing committee here in the room, Marco and Ralph, myself, and then a couple other people. Harut is also here, Keith, and usually from UVA. So it's going to be March 14 to 16, which is Thursday to Saturday at Duke University, which falls into the Duke spring break.